Hello everyone, and welcome to our presentation entitled XORBoost, Tree Boosting in the Multiparty Computation Setting. The presenters are Marc Desgroseilliers and Marius Vuille, and we both work for a company called Inpher that is US and Switzerland based. So, a small overview about this presentation. First, we're going to talk about tree-based learning. So people that are already familiar with that, it will be more like recalls. Then we're going to explain how we adapted this to the MPC setting. And in the end, we're going to show some benchmarks and results. So what are our model assumptions? So first of all, we have a passive security model. So the honest and curious security, meaning that all the participants, they faithfully execute the protocol, but they still try to learn everything that they can from the information they're given. We have full threshold security. We assume that the number of players is rather small, let's say not more than 9-10 participants. And we do support both horizontal and vertical stacking of the input data, and even a combination of both. So, a small reminder about tree-based learning. Suppose you're given a dataset X. Let's say it has capital N samples, so each sample being a row of X, and it has K features, so K is the number of columns. And let's also suppose here that we have fixed for each column, we have a fixed number of threshold values, which is typically much smaller than capital N, could be 100, 200. So for each column, we have the same number of threshold values that we have fixed. And we also have a response vector, capital Y. So a tree is basically a function from R to the K to R, which is evaluated in the following way. So let's give it a little x. So this is a sample, a row of capital X. You would first take its J1th coordinate and compare it against the threshold T1. If the predicate is satisfied, you would go to the left. Otherwise, you would go to the right, and then you would say evaluate the J2's coordinate of X against the threshold T2. And then depending on the outcome, you'd go to the left or to the right. And those WI's, these are scalars. So this would be the value or the evaluation of your function. So obviously, a tree could be much larger than this, could be quite asymmetric in case it got pruned. And you should also keep in mind that you can have several trees. You can then evaluate them individually, and then your RK to the R function would just be the sum of these values of all the evaluated trees. So let me talk a bit about XGBoost, which stands for Extreme Gradient Boosting. First of all, why are we interested in this algorithm? Because it kind of it got quite popular by winning a couple of machine learning competitions. So people are quite interested in this algorithm. What is the objective? So let's say you have a loss function, which comes from the task you want to achieve. Could be regression, or you want to do classification. And you want to determine trees, you want to grow them, we say, in order to minimize this loss function. And what does boosting mean? So unlike random forests, where, for example, you would grow several trees simultaneously, in boosting, you do things successively. So your model is always a certain set of trees, and once you have determined the tree, you would add it to your model, and then it would not change anymore. So first you start with 0 trees, you grow 1 tree, you put this tree to your model. Then you start growing a second tree, and you would add the second tree to your model, and then this doesn't move anymore. And given a fixed model, which is the tree that you would add to your model? Well, the one that yields the largest loss reduction, obviously. And so we do so by determining all these J and T values of an approximation of your loss function. So obviously this rings a bell. It's nothing else than a second order gradient descent that we do in order to determine J and T. And a bit more precisely, what does that mean for a given node? So as we said, we have number of features columns. And for each of those columns, we have a fixed number of thresholds, so typically 100, 200. And for all of these candidates, we compute the loss reduction that one would obtain by choosing this split. So by split, we mean J and T. And since we do a second order gradient descent, we have a closed formula for the weight, so these W's that you would attach to each split, which gives you also a closed formula for the reduction of the loss. So you can really compute this explicitly. And then we determine J star and T star that maximize this loss reduction. We do so by an Oblivious argmax algorithm. And then we're going to determine amongst all samples in the node which ones do satisfy the predicate xj star less than t star. For those who do satisfy, we send them to the left child. For the other ones, we send them to the right child. And then obviously for both these nodes, we're going to do the same thing again until we have reached the desired depth, where we have our weights that we obtain by this closed formula coming from a second order gradient descent. And then we're done training. So now my colleague Marc is going to tell you how we adapted all those ideas to the MPC setting.
Let's now discuss how to adapt XGBoost to the MPC setting. First of all, the indices, threshold values, and prediction values are going to be secret shared. That means that the training operation for the machine learning model does not reveal any information about the original dataset. Threshold candidates, so these T values, are obtained by a sorting algorithm and extracting specific rows. I'll go into a bit more detail on the next slide. For each node, we need to keep track of which sample is to be considered for this node, and we're going to do this through the use of a 0,1 indicator vector for each node. We fully grow the tree to full depth, so the depth is a parameter of the algorithm. We grow the tree fully, and then we have a procedure to obliviously prune the predicted values. So we prune the branches of the tree and adapt the predicted values to if the branch is pruned or not. And finally, one last thing to note is that to compute the loss reduction for the different entries of the matrix to which we will apply the argmax, we require a private division algorithm. So I mentioned that we need a sorting permutation. This is going to be done through an Oblivious quicksort. Here's a quick overview. So first of all, for each column, you apply a uniformly random permutation. And then you apply the quicksort algorithm. You need to do comparisons with the pivot. You will not reveal the values of the array that is to be sorted, but instead you will reveal the result of these comparisons. And by the fact that you apply the uniform random permutation, this does not reveal any information about the original data. With these sorting permutations in N, we're going to call them pi j, and this allows us to have the threshold values because they're in the sorted matrix. They're going to be at a fixed position in the sorted matrix. So that's great. A few more details about the indicator vector. Here's an example. So you see you start with a all one indicator vector because you consider all the samples, and then only a subset of the samples are considered in the left and the right child. So then the question is, how can you update these indicator vector? If I give you the indicator vector of a node, and you would like to compute the indicator vector of the left and right child nodes, then how are you going to do this? Well, we're going to consider these bucket vectors, which have all ones and then all zeros, and so these would be if the value is less than the Bth threshold, then it's a 1. If it's greater than the Bth threshold, then it's a 0. And if you think about it, if you have the J star and the T star, the entries that need to go left, those that satisfy the predicate, they will be exactly pi j inverse of the BVB. So you apply the inverse of the sorting permutation to this bucket vector, and that's going to be the trick. That's using this vector. This is what is going to allow us to update the instance vectors, the integer vectors. So the one trick that we use to speed up the computation is, instead of computing all of these pi j inverse of BVB for all features and all buckets, we're going to compute log B generator vectors and then use these to compute the required PJ inverse of BVB. If you want more details about this procedure, you can go in the paper, but the idea is that instead of having B vectors, we use only log B vectors, and that results in some speed up and some gains. And so finally, some benchmark data. So you can see if you, here the results are for the wall time and for the memory according to the dataset size. So as you can see, even for large datasets of 100,000 by 300 features, the time stays at around 4 minutes per tree, which is quite reasonable, given that usually XGBoost models, they range in the hundreds of trees. And here you can also see the dependency on the number of buckets and the tree depth. And as expected, the wall time and memory requirements, they increase with tree depth and number of buckets. Thank you for your attention.